Good morning, student. In the last part of the video, we have mentioned about different harmonics produced on a fixed string, where both ends of the string are fixed. For example, in the first harmonic, the position of the string should be like that. This is the first harmonic. So both ends are the fixed. Okay, and this is the position of equilibrium, and these are the position of nodes, right? Nodes here, and this is antinode, and the length of the string was lambda by 2. Okay, and the position of the antinodes were lambda by 4. Okay, this is known as the first harmonic. Okay, and in the second harmonic, how much length of the string we choose? It was lambda, right? So length of the string in this case was lambda in order to excite the second harmonic wave. So second harmonic was something like this. This length was lambda, and of course this is node, and this is also node, while these are antinodes, right? And the distance was, this is lambda by 4, and this was 3 lambda, and 3 lambda by 4. Okay, 3 lambda by 4. This way we have excited different harmonics of the string. But you see, we cannot choose the length in order to excite the first harmonic or second harmonics of the string, because length is a parameter which can be arbitrary. We don't know what will be the wavelength before choosing the length, right? So length is not a parameter which we should concentrate in order to excite the first harmonic or second harmonic or the third harmonic of the string. The parameter which we control in case of string vibration is the frequency of the string. That is the parameter which we can control, frequency of vibration, right? Because the mechanical vibrator which we use to produce the incident wave is fixed here. So basically we can control the frequency of that mechanical vibrator and the vibrator. Therefore, what we want, that our control parameter should not be the length of the string to excite the harmonics, right? Length should not be the control parameter. Should not be the control parameter. Rather, we want the frequency to be the control parameter, so that we can hit a particular frequency to produce this kind of harmonic, first harmonic or second harmonic or third harmonic. This kind of parameter we should able to produce by choosing a appropriate frequency. Okay, so we want frequency to be the should be the control parameter, because we can control frequency very easily. Nobody wants to control the length. You give me just any length of wire, I want to choose a frequency so that it can excite the first, second or third harmonic, etc. Okay, so frequency should be our control parameter. And this frequency at which we will get this first harmonic, second harmonic, third harmonic, fourth harmonic, etc. all these frequencies are known as the resonance frequency. These are known as resonance frequency because when we excite first or second or third harmonic, the amplitude of the standing wave become maximum. As one can see, the displacement of a standing wave was twice a sine kx into sine omega t. So you see, when kx is maximum or minimum, then the amplitude of the wave was twice a. So this is the maximum or minimum, that means extremum amplitude wave. Okay, so the frequency which excite this maximum amplitude wave, these are known as the resonance frequency. Okay, so in practical life, what happens is that we the tune the mechanical oscillator fixed at the other end of the string, and one for particular frequency, say omega, and these are known as the normal mode or resonant frequency. One can observe the formation of this kind of harmonics. Not for every frequency you can observe this kind of harmonics. That means not for any frequency which we can choose we can have the formation of standing wave. Only at a particular values of frequency we can see the formation of such kind of wave on the string, and these frequencies are known as the resonance frequency or normal modes of vibration of the string. Two names are there: resonance frequency with respect to the applied one, normal modes of vibration when we express with respect to the vibration of the string. Okay, so both these terms are quite equivalent: resonance or normal modes of vibration of the string. Okay, these normal modes exist for all kind of oscillating system, not only for string, even for sound. I mean, all kind of musical instrument, these normal modes exist. Okay, so basically what we are going to find, we are going to find out these normal modes of vibration. Okay, so for that, what we are going to do, we are going to apply the boundary condition. Boundary condition, very easy to apply the boundary condition in case of a fixed string, because you see this both end of the string is fixed. Suppose we take any arbitrary length L of the string. L we don't know, it can be 1 meter, 1 centimeter, doesn't matter. Okay, but you see when both end of the strings are fixed, then it means the displacement of the string at this 2 point will be equal to 0. Okay, because these two ends are fixed, therefore the string cannot vibrate at that point. Okay, so this displacement y will be equal to 0, say at x is equal to L, where L is our length of the string. Now we want to find out the frequency corresponding to this length. Okay, so when y is equal to 0, that means this quantity sin kx will be equal to 0. It's not it, because this quantity anyway cannot be 0, so twice it's amplitude only, so this thing should be equal to 0. So this is, say, sin k n into pi, where n is equal to 0, 1, 2, dot 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 dot. Okay, so we can write kx is equal to n pi, and k we can write twice pi divided by lambda. Okay, or since we are interested in frequency, therefore k we can write omega n divided by c into L. L is the length of the string, is equal to n pi. Therefore omega n is equal to n pi c over L. Okay, so these are our normal modes of vibration. Okay, now you will see when we choose n is equal to 1, we can get exactly L is equal to lambda by 2, because L is equal to lambda by 2 was our condition for first harmonic generation. So how can we obtain that condition from this resonance or normal modes of vibration? Okay, so let's do that calculation. Okay, so we have got omega n is equal to n pi c over L, where L is our length. Okay, so for for n is equal to 1, that is for first harmonic, omega 1 should be equal to n or pi into c over L. This is the value of omega 1. So let's say length L is equal to pi c divided by omega 1. Okay, so L is equal to pi c, then omega is nothing but the frequency is nothing but we can express frequency with twice pi c by lambda, right? Because omega is equal to twice pi nu is equal to nothing but velocity of the transverse wave divided by wavelength. Okay, so what we can write, twice pi c over lambda. So lambda will be here, so pi c gets cancelled out, therefore L is equal to lambda by 2. Okay, so when we choose omega is equal to pi c over L, then we know what is then we can have L is equal to lambda by 2 and first harmonic is excited. Okay, so omega 1 say first harmonic frequency pi c over L, because we can easily determine what is the velocity of the transverse wave, because velocity c is equal to, we always know, t by rho. Okay, so if we know the tension in the string and if we know mass per unit length, then we can easily choose the velocity. Once we know the velocity, then we can prove that L is equal to lambda by 2, and it will automatically excite the first harmonic of the string vibration. Okay, similarly omega 2 will be equal to, for second harmonic, twice pi c divided by lambda, so that gives L is equal to twice pi c divided by omega 2. Then just put the value of omega, twice pi c, and then omega is equal to twice pi c by lambda. Okay, c cancel out, twice pi cancel out, therefore L is equal to lambda. As you can see, as I have told you, L is equal to lambda will give us the second harmonic. L is equal to lambda by 2 will give us the first harmonic. Okay, so in this way we can choose the frequency, the value of omega, and by that we can have the control over the frequency generation, thus first harmonic, second harmonic, third harmonic generation of the wave. Okay, so omega n is equal to n pi c divided by L. These are known as the resonance mode or normal modes of vibration. Resonance or normal modes of vibration of the string. Okay, here we can have the formation of standing wave, and the standing wave are always the maximum amplitude wave. Okay, so with this, now our control parameter has been shifted to L to omega n, and just the mechanical vibrator you have to tune, and whenever the mechanical vibrator satisfies this condition, omega n is equal to n pi c over L, we can see the formation of the standing wave on the string. Okay, so not for every frequency we can excite the standing wave, only for resonance or normal mode of vibration of the string, only at those frequency we can have the formation of standing wave on the string. That's why when two people just fix a string and they vibrate at any frequency, they are not going to see the standing wave formation. Okay, one have to be very careful while choosing the frequency. Only at this particular value of frequency one can observe the formation of the standing wave. So it's a little hard business than you could have imagined. Okay, so we have to choose always the right frequency to get the this resonance or normal mode or the standing waves on the string. Okay, so with this, now we are going to determine what are the values of those what are the values of energies for this particular for this standing wave. Okay, we know when the standing wave will excite in a string. Now we are going to find out the total energy of such kind of wave. Okay, so we know y is equal to, what is the value of y? Y is equal to twice a sine kx into sine omega t. This value we know. Now what will be the value of the kinetic energy? Kinetic energy will be equal to half into, you see, mass per unit length is rho, therefore mass of a small element will be rho into dx. We have to multiply it with the velocity, right? So half mv square, this is m, this is v square, and v we can write dy by dt, right? Dy by dt whole square, as I have always written. So it will be rho dx del y by del t whole square. So this is the value of the kinetic energy of the string, and we have to integrate it towards the whole length of the string, 0 to L, this value. Okay, then potential energy of the string, half into 0 to L tension in the string, then as if you have remembered, T into del y by del x whole square into dx. Okay, so this is the tensor potential energy of the string. So basically what I am going to do, I am going to differentiate y with respect to x and t, because kinetic energy involves del y by del t and potential energy involves del y by del x. Okay, and we are going to put this value to find out the value of potential energy and kinetic energy for this string in order to have the total energy of the string. Okay, so let's do that calculation. So y is equal to twice a sine kx into sine omega t. So y dot is equal to, let me write this as del y by del t so that it doesn't have any confusion. So twice a sine kx omega into cos omega t. Okay, so twice a omega sine kx into cos omega t. Okay, so del y by del t whole square will be equal to 4 a square omega square sine square kx into cos square omega t. Okay, now let me find del y by del x. Del y by del x will be equal to twice a k and then cos kx into sine omega t. Okay, so del y by del x whole square will be equal to 4 a square k square cos square kx into sine square omega t. Okay, these are the values of del y by del x whole square and del y by del t whole square. Okay, now the kinetic energy half into 0 to L rho into dx del y by del t whole square. Put this value half rho, we can take it out because this is a constant. 0 to L dy by dt is equal to 4 a square omega square sine square kx cos square omega t. Okay, this is the value of del y by del t whole square into dx. Okay, now you see cos square omega t, this term is the constant with respect to the variation of dx, so we have to take it out from the integration sign into 4 a square into omega square. Okay, so cos square omega t 0 to L sine square kx into dx. Okay, so this term is constant with respect to differentiation with respect to x, so basically we have taken it out. So this will be 2 rho a square omega square cos square omega t, and this thing we can express as half into 1 minus cos 2 kx dx 0 to L, right? Okay, so this value what we will get 2 rho a square. Okay, omega we can write this as omega n because we know that for only normal modes of frequency the standing wave will excited. So omega n cos square omega n into t, and then this value will be, first value will be half into the integration dx L minus 0 minus cos, when we integrate we'll get plus sign, right? So this is sine kx over k, upper limit is L, lower limit is 0. Okay, okay, so this value is basically okay, so for half. Okay, so this value is basically so rho a square omega n square cos square omega n into t half into L plus 1 by k sine kl sine kl minus sine 0 is 0. So I am basically not going to write it. Okay, now we are going to find what is the value of sine kl. As you can see, sine kl is equal to sine twice pi over lambda right? And the length of the string, as you can see, as I have already told you, for excitation of standing wave, L should be always equal to, L is equal to lambda by 2. We have found it. Then lambda also we have found it for third harmonic, 3 lambda by 2. Right, this way the values of L should be. On other values of L we cannot have standing wave. Okay, so now you see this, if we multiply by this lambda by 2, then what we will get? Lambda lambda cancel, 2 cancel, sin pi is always equal to 0. Okay, for this we will get 0. And then let's try for L is equal to lambda. Then you see sin twice pi over lambda, L will put lambda, right? So L, this get cancel out, so this is equal to 0. So in this way, for every value of again try for sin 3 pi by lambda. Let me show you. Sin 2 pi by lambda, and here L is equal to 3 lambda by 2. 3 lambda by 2. So 2 get cancelled, lambda get cancelled, sin 3 pi is always equal to 0. Okay, so for all values of L, sin KL will give us 0. Therefore, we have to basically neglect this term. Okay, so now what will be the value? This thing multiplied by this thing. Okay, half get cancelled out. So this value will be equal to rho a square omega n square cos square omega n into t into the length of the string. Okay, so this is the value of the kinetic energy which we obtain for such kind of normal modes of vibration. Normal modes of vibration. Okay, these are the expression for kinetic energy when the string operates in its normal modes of vibration. Okay, similarly we can also calculate the value of potential energy. What is the value of potential energy? Potential energy was PE is equal to half 0 to L T del y by del x whole square into dx. Okay, so it was the value of the potential energy, and I left it as a homework problem because here you have to the tension of the string, you can express it with respect to rho and c. Okay, don't write T, you just can replace T with respect to rho and c as we have found in the earlier classes. Okay, this is the first thing I am going to give you, and then put the value of dy by dx, and when you do all the calculation, then you are going to find out the exactly same value as is the potential kinetic energy of the string. Okay, so the potential energy of a string should be exactly equal to the kinetic energy of the string, and it should be in the same phases. This is the case which already we have found for any vibration of a string in the previous part. Here also we are going to get the same part. Okay, so this part of the problem you have to do it by yourself, and you are going to get exactly the same value of the potential energy of the string. Okay, so kinetic energy and potential energy in case of a string have the exactly same value, and they are always in phases. Okay, so with this, let me write the value of the total energy of the string when it's vibrating normal modes, or when there is a formation of standing wave. Total energy will be equal to rho a square, right? Rho a square omega n square into L. So this value is cos square into omega t. Okay, and this value you will get same, and in place of cos square omega t, in case of potential energy, what you will get, this sin square omega t term will be there, because you see del y by del x contain sin square omega t. Okay, so in case of potential energy, you will get sin square omega n into t. Okay, so you have to basically add this up, sin square omega n into t. This is omega n, so this is value is 1. So rho a square omega n square into L, this is the total value of the energy. Total value of energy of the string of length. Okay, now you see one thing very clear here, we don't have to do any time average of the total energy, because now you see since this is a standing wave, it doesn't vary with time. That's why we will get we don't need to do any time average, because time average we always do if it's vary with time, because but standing wave its position are always fixed. It does not vary. The x position of the minimum and maximum amplitude or the zero amplitude, it never changes with time. So we don't need to do any kind of time average for this total energy. This already is a time average. Okay, and that value what we have obtained, rho a square omega n square into L. Okay, so this is the expression for total energy E. E is equal to rho a square omega n square into. Okay, so it's depend on the normal mode of vibration of the string, amplitude of the string, and mass per unit length of the string. These three quantity will collectively determine the total energy of vibration in normal modes of oscillation. Okay, so thank you.